So the whole webinar is planned to last about 1 hour and 20 minutes with 2 QA and break sessions where you can post your questions or raise your hand in order to open up the mic and ask your questions in the 2 breaks. So what is the COIN-3D project? Is regarding research and knowledge exchange activities in the area of 3D VLSI. So we have a lot of actions that we're going to perform. We have conference and workshop. We have the visiting researcher program, training programs with summer schools, webinar, and advanced training courses that will happen to University of Thessaly. We have several early stage researchers. We have participating administrative task and technology transfer office, where we through these webinars as summer schools, we're going to produce some networking and collaboration opportunities. So the consortium of the COIN-3D is from University of Thessaly that is currently coordinating the project. Is University of Bremen from Germany, University of Amsterdam from Netherlands, and University of Glasgow that is hosting the today's event.
Hello. Yeah, so in order to know how we can apply AI in chiplet reliability, we need to understand what we mean by AI. So actually AI, it's just the science of make things smart, or to be more specific, AI, it's like a technique which enable machine to mimic human behavior to learn and solve a problem. All AI actually about learning. So when we talk about us as a human, we have like intelligent behavior. For example, when we talk about doctors with medical diagnosis or something like this, we expect from us to human to learn some task and try to like classify some disease or something like this. But actually, when we talk about machine, we need to make this machine learn some algorithm or some models in order to have the final product. It's like a robotics or something like machine have like higher reliability like people or more accurate than people. So, in order to see how we are think and try to solve problem as intelligent people and how machine learning work, we need to see this example. For example, here, if we have X as an input and have Y as an output. For example, here we have 1, then we got 1, and if we have 2, we got 4, then if we have 3, then we got 9, then 4, 16. For example, here, if we have 5, what we expect to have, according to our brain as a human, we expect to have like Y equal x squared, because we as a human try to distinguish the relationship between or to study the pattern between the x and y. So here as a human we only try to extract some pattern. So in the same problem, how machine learning can solve this problem? Actually, machine learning need to learn algorithm or program to extract this pattern. So we will have now example to see how the machine learning solve the same problem. So the machine learning actually following statistical learning algorithm to solve this problem. So in the following diagram here, yeah, here in this diagram, it will have like first the data that we had as a people. Then this data, it will be input for a machine learning model. Then the model will try to learn specific pattern between the input and the output to have the model, and then use this model to the inference or predict a new value for a previous value. So here, for example, when we have, yeah, can I? When we have like here 5 as an input, then we will have like 25 as an output. This is how the machine learning solve a problem compared to us as a people. The machine learning need to go through all these steps, even with different algorithms. All of machine learning follow this step. So here the learning, it will have like the training phase and the inference phase. So in the next slide, we will talk about the machine learning algorithms. Actually, we will have like 3 kinds of machine learning algorithm. We will have first the supervised learning. In the supervised learning, we will have the X and Y as input to the model, as the previous example. We have here 2 kinds of machine learning algorithm. We could have the classification that try to classify different classes like disease classification or data classification. And we also could have the regression when we try to find the relationship between 2 or 3 patterns. Then the unsupervised learning. In the unsupervised learning, we could have the clustering. In the clustering, we try to grouping the clients according to their similarity to different groups. Finally, the reinforcement learning. In the reinforcement learning, it's actually like agent, and this agent try to interact with the environment. This agent will be like in specific state, then it will take specific action, and then it will get specific reward. Actually, according to the data that we can deal with in machine learning, we can actually deal with images, and we can deal with text and with numbers and audio and video. But actually, machine learning is considered more suitable to deal with numerical data, because in machine learning we need to extract the features by ourselves. So this is can be very complicated to images and audio and video data. And also machine learning is considered suitable to deal with a smaller data set. And finally, when we talk about complex data forms like images, audio and video, we prefer to use a more complicated technique. Now let's have another branch of artificial intelligence or AI, which is the deep learning. What we mean by deep learning? Deep learning actually it's like kind of method that try to mimic our brain as a human and the connection between neurons. Let's us break this definition to 2 parts. First part is the neural network. According to the neural network, it will have like input and like hidden layer and the output. But actually, when we talk about deep learning, it's like the same as neural network, but actually it is with like a huge or many hidden layers in order to deal with more complicated scenarios. Yeah, so here how deep learning work. As we said, deep learning consider more suitable to deal with more complicated data like images, video, and audio. And here we will focus on images to see how deep learning solve the problem. First, for example, we have like a labeled image. This image will be input to the model, and the model will extract the feature, and then the model will be trained, and this model will be used to predict the output for a new samples or a new image according to hot encoder, and will be the output. Now, for the deep learning, we could have like 3 kind of deep learning models that can be used. There is the convolutional neural network that considered suitable to deal with images, and we also could have the current neural network that considered suitable to deal with the serious time data, and Also, we could have the LSTM that consider more advanced to deal with the time series data. And the main advantage actually to the AI to be applied in many methods, it's considered speed and efficient, and it can deal with massive amount of data and more accurate and less error. And according to the type of data that can be solved or deal with it in deep learning, we can deal with the images and yeah, we can deal with images, audio, video, and it's not like perfect to deal with numerical data. Actually, in deep learning, we don't need to extract the feature by ourselves. It's something will be doing by the model itself. And also, deep learning consider very suitable to deal with large data set. And finally, it's considered very suitable to deal with advanced problems like large language models and image recognition. Now, how can we apply deep learning or AI in general in chiplet design? Let's see in the next slide how we can do this. Actually, when we talk about the traditional design that based on a human to do specific job, it requires significant amount of effort to be doing, and also it's considered labor intensive and time consuming, and also it's depend on the human experience to be doing, and the most of the time it's considered less accurate and less efficient and more vulnerable to the defect. According to the eye design, it's considered like automated repetitive task, and it is not needed to do one by one. And also for AI, it's take more less time to execute specific task, and also it's considered more efficient and less defect. And there are many algorithms can be applied in this field like GAN and deep neural network and convolutional neural network reinforcement learning to solve different problems in chiplet design. According to utilize AI to optimize various stage, it can help to optimize the design stage in order to balance between the power, perform, and thermal constraint. And also, it can be used in manufacturing procedure in order to define, for example, defect according to previous data or the previous information. And also, it can be used to improve the interconnection enhancement and the thermal management and power efficiency and standardization and capabilities. And also, finally, it can be used to solve the placement problem.
Okay, hello everyone. I'm Yixian from University of Amsterdam. Today I'll be discussing the thermal challenging in EDA. Let's start by reviewing traditional chip design flow, which comprises 5 main stages. First is the specification phase, where we design the chip's functionality and the critical constraint, such as thermal limits and power targets. Next is the RTL design, where the chip's behavior is described at an abstract level using hardware description language like Verilog. This bridges the logical functionality of the chip with its physical implementation. The system, the synthesis phase follows, where the RTL description is transformed into a gate-level netlist, serving as the blueprint of the chip at the logical gate level. After synthesis, and we move to the physical design, where gates are placed and wires are routed, and the design is optimized for timing, power, and also area. And finally, In the verification phases, we ensure the chips function as intended, meeting all the defined requirements and conditions. While this flow is effective and it faces growing challenges as performance demands increase, the increasing number of transistors in modern chips lead to higher power consumption and heat generation. With more transistors packed into small area, power density increase, creating localized hotspots that are difficult to cool effectively. This is not only affect the performance, but also reduce the chip's reliability as prolonged high temperature accelerate opponent degradation. Traditional method like DVFAs, dynamic voltage scaling and frequency, dynamic voltage and frequency scaling, and also is typically not enough to handle this challenge, especially for the high performance design, necessitating the advanced thermal management techniques. One of the critical thermal challenge in modern chip design is the dark silicon phenomena. This occurs when only a fraction of cores on a chip can be active at a given time due to the power and the thermal constraint, while the rest must remain inactive or dark to prevent overheating. These limitations significantly reduce the chip's utilization, creating challenge in achieving maximum performance. To solve these issues, techniques like task or thread migration and advanced thermal management are often employed. Next, I will introduce examples of both an analytical method and a machine learning approach for thermal management through thread migration. We run. This is a simple example. We run 2-thread Black-Scholes workload on a 16-core system under thread rotations to prevent the thermal violation. For example, for the 2 threads were initially assigned to core 5 and core 10. Then we rotate it periodically, and the period is 500 milliseconds, and they can make the heat evenly, and we can show the trace. We can show the trace here. They can balance the temperature and while maintaining the system performance. However, it requires extensive analysis of system characteristics, such as the cache latency and each core's heat dissipation conditions, make it highly complex. Determining the rotation speed, the period involving formula sophisticated equations. While this analytic model can work well in specific scenarios, they have significant limitations. They require extensive pre-analysis of each floor plan and workload, make them inflexible for dynamic workloads or real-time adjustments. To overcome these challenges, machine learning-based approach provide a more flexible and generalizable solution for thermal management. Let's explore this by this new the machine learning-based thermal management approach. This machine learning-based approach, we start by collecting the data from the application simulations using tools like Hotspots, which evaluate tasks on the various operating points, including the power budget and configurations. And then the thread, we collect the thread execution trace, such as the IPAs, the instruction per second, and cache performance data, and are extracted to create a training data set. And we use a lightweight 3 neural network to capture this relationship. Once this model is trained, and the model can predict the optimal core mapping and migration strategies during the inference time, and it can generate well, eliminating the need to exclusive pre-analyze for each floor plan. Machine learning provides a powerful and scaling solution for thermal management and make it efficiently do the heat dissipation. Thanks for your attention, and we are happy to take any questions you may have.
Okay, actually, let's have example of utilize AI to optimize various stage of chiplet design. So we will start with the first thing, which is the lithographic hotspot detection. Actually, it's considered manufacturing procedure. So when we talk about new smartphones or smart devices in general, like iPhones, watch, laptop, all of these devices use modern chip with advanced technologies such as 5 nanometers or smaller in some cases. And these chiplets or chip, it can have billions of transistors in order to enable different features like AI acceleration, high performance game, multi-core computing, low power consumption, and more capabilities. But actually, when we talk about all of these features or these attributes in 5 nanometers, we could have something called feature shrink. The feature shrink can lead to a specific problem or significant problem, which is the manufacturing defect. Manufacturing defect, it's mean having a defect in the final stage of the product, and will be very costly. So there are many methods have been proposed in order to overcome the defects in early stage or solve the defect in early stage before the manufacturing stage. The lithographic, actually, one of these methods has been proposed to find the defect in early stage. In the lithographic, actually, or lithography, actually, we try to create extremely tiny structure on the semiconductor wafer, or actually we can say it's like printing a specific pattern on the surface to define where the component of chips will go. For example, here in this image, we can see in the mask, we can have like specific patterns or layouts that we want to print on the wafer. So in some case, as a result of neighboring patterns or the feature shrinks, we could have like some of hotspot in the lithography. What we mean by hotspot, for example, if where we can see here on the black images, we can have bridging or branching. This kind of lithographic hotspots, it's considered undesirable patterns, and if we don't solve these patterns in early stage, it will be printed on the wafer, and then we will have like manufacturing defect. So we try to find this pattern in early stage. So we can have like a final note from here, like finding the hotspot in early design stage is mandatory to avoid any undesirable layout pattern in the manufacturing stage. So in the next slide, we will talk about using the convolutional neural network. As we said previously, it's considered suitable to deal with images. So in the convolutional neural network here, we try to have like these layouts or these patterns as an input for the model, and we try to have like a specific model or detection model to an image or specific layout is hotspot or not hotspot. Let's have zoom on how this model works. First, we will have like lithographic hotspot images, and these images will be changed to pixels, and these pixels will be moved to the model in order to extract the main features. Then build the deep learning model or convolutional neural network models, and then we will have a classifier model to classify if specific image is hotspot or not hotspot. So this is the model, and according to the result from the paper that proposed to using deep learning to solve this problem, they got this result actually according to the model accuracy to define whether an image it's hotspot or not. They got like around 100% or 99% of accuracy, and according to the loss of the model, it was like very close to the zero, and all of this during just 18 training rounds. And in general, we can say by applying AI in this problem, we can introduce an accurate, fast, cheaper, and reusable hotspot detection framework. So now we will use also deep learning in order to solve another problem. Here we will talk about BGAN. Here BGAN consider optimization problem. We will talk about benchmark scarcity. First, when we talk about design a new EDA algorithm or design a new tools, we need to have like benchmarks in order to evaluate or validate the proposed method compared to the previous method. For example, when we talk about benchmark that can be used to test algorithm or test a new method to optimize power delivery network, we need to have benchmark to evaluate the new method. So actually the benchmark, it's like not something it can be easy to be available every time, because when we talk about benchmark for chiplet, we could have like epsilon's problem. What we mean by this, for example, when we have like a new design for chip with like less than 5 nanometer or with new materials, using a previous or old chip with another design or another material, it cannot be like valid to evaluate a new method. So we can't use only old benchmark to evaluate a new method. And also when we talk about new chiplet design or something like this, we could have like a confidential problem because some companies, they can't sacrifice their data or like designs in order to have it like a benchmark. And also the design, it's like improved very quickly, and this makes it labor intensive to have all of these benchmark available. So here in this paper, they proposed to using GAN to generate realistic benchmark for BDA design in order to test and validate new methods. Actually, for the BDA benchmark, it's actually like a tool or method to evaluate the new design for AI drop and electromigration. In this paper, actually, they used the generative adversarial network to extract specific feature from the current map and train model in these features in order to generate a lot of new benchmarks that can be used to validate new methods. Actually, this paper based on the generative adversarial network that known as a GAN. And what we mean by GAN, actually GAN, it's like a deep neural network method that consists or contains 3 parts. The first part, it's the generator that's responsible to generate fake images or fake data. And that discriminator is like another part of the GAN. It's responsible to distinguish between the images generated by generator. Are these images real images or fake images? All of these generator and discriminators based on the networks in order to train models to the generator to generate much better images, and for the discriminator to be much more better to distinguish between the images. Now let's see how GAN works in training. For the generator part, actually, it's started noise or like Latin vector generated by GAN, and this generated vector, it will give us like a noise images, and for the real images from the real data set, and the discriminator always try to distinguish between the real images and the fake images, and according to the discriminator performance, it can say this is real or fake images. Then we will have generator loss, and we will have also the discriminator loss. So in both of these loss, it will be fed again to the model in order to improve the capability of the generator and the discriminator. But actually, when we talk about GAN, we talk about model need a huge amount of data to be trained. But actually, according to this problem, we only have a few amount of benchmarks, and we can't provide the model with all the amount of data needed to train GAN. So in the next slide, we will see how we can have enough data to train GAN model. So due to we don't have like enough data to train GAN, we will use transformer learner to train GAN on source data, and then fine-tuning the model on the target dataset. Let's see what we mean by this, because we have only few amount of data for the benchmarks. We will try to find some data can be very similar in the features on the current map data. Here, when we talk about current feature or the current map, we can find like here on this images, they try to find something similar. They used the satellite, urban satellite images generated by Google Map in order to use it as a source data set. They tried to do like some pre-processing in order to make it fit very well to the training. And in general, they had like 4,167 images. And according to the target data set, they only had like 10 current map or 10 real images that can be used in the fine-tuning stage. Let's see in the next slide how this has been doing. Actually, in the training stage, they started by the source dataset for the urban satellite images for the 4,000 images before that we had. Then they trained like GAN models. Then they moved the model through the transformer learner to the to fine tune it on the real images for 10 current maps, and this is gave us like a model or GAN model has been able to generate enough current map images to be used in the BDA. So in the next slide, we can say in this we can say by using GAN, we can overcome the data scarcity and the benchmark scarcity by generated enough images to train a new to train or to validate a new method. And also with the GAN, we don't need to train model on a lot of data. We can use transformer learning in order to solve this problem.
Okay, hello everyone from me also. My name is Olympia Axelou and I am postdoctoral researcher at the University of Thessaly, Greece. I'm really excited to talk to you today about a very interesting cutting-edge topic, that is how machine learning is transforming thermal and tire drop analysis in VLSI design. The goal of my talk is to showcase some advancements and maybe spark some conversations about how we can leverage this method in our current work. So let's go. As technology advances, the growing demand of Internet of Things applications in fields like medicine, aerospace, automotive pushes for miniaturization of chips and forces VLSI design to become increasingly complex. Due to this, we are facing a number of critical challenges like managing power integrity and thermal performance, which are becoming increasingly critical, especially when migrating to 3D chiplet-to-chiplet architectures, where we first need to perform die-centric analysis in every chiplet. Hotspots and IR drops caused by localized heating and uneven voltage distribution are becoming more significant as they can compromise both performance and reliability, and as a result lead to long-term reliability phenomena like electromigration, accelerating wear-out mechanisms and reducing chip lifespan. Adding to this, traditional simulation methods for addressing these issues are becoming bottlenecks, as the existing full-chip thermal and tire drop simulations are computationally expensive, often requires hours to complete. And of course, in the fast-paced semiconductor industry of today, delays in design cycles can mean lost opportunities. In particular, lengthy simulation runtimes and iterative bottlenecks slow down innovation, making it harder to hit competitive product launch windows. So with time to market pressures growing, we need to find solutions that are faster and more efficient than the ones that we currently have. But what's the problem with the traditional methods? Traditional techniques such as finite element analysis and thermal RC network modeling are highly accurate but come to a high computational cost. These methods require solving large systems of equations, making full chip simulations time-consuming, and ultimately becoming a bottleneck, especially for large-scale VLSI designs with billions of nodes. On top of that, of course, there is the trade-off between accuracy and scalability. To achieve precise results, simulations can take hours or even days to complete, time that designers simply do not have. And in traditional analysis, iterative approaches are commonly used to refine results, but they come at a significant cost. This becomes a major bottleneck, especially when designers need to explore multiple what-if scenarios, what-if analysis, such as adjusting power distribution or modifying the layout to improve thermal performance. So to meet the competitive time-to-market demands, designers need to find tools that deliver accurate results at a fraction of the time. And of course, this is where machine learning comes in. Researchers have shown that we can utilize convolutional encoder-decoder networks for thermal and tire drop predictions. The concept is to reframe complex simulations as image-to-image or sequence-to-sequence translation tasks to simplify and accelerate the analysis process. In particular, the proposition is to employ two types of networks for different targets. First, for static analysis, encoder-decoder architectures like UNets, which are ideal for efficient image-to-image mapping, and LSTM networks for transient analysis, which can handle very well time-dependent scenarios like transient thermal effects or IR drop variations. And how it works is that the network takes as input power distribution maps and PDN characteristics, and it generates high-resolution thermal and tire drop maps in milliseconds and with very low relative error. In particular, the method takes as input the power distribution that captures the localized global and power dissipation patterns essential for identifying hotspots, the PDN density that represents the granularity and the robustness of the power grid, and finally, the effective distance to power pads that quantifies the resistance between the circuit components that are underneath and the power pads. And the output of the model consists of very accurate temperature and voltage drop maps, providing insight into areas of high thermal stress and tire drop. Thermal maps visualize the temperature distribution, and so they highlight potential problematic zones. These maps are generated rapidly, enabling real-time feedback compared to traditional methods that take up to hours. As a result, It reduces analysis bottlenecks during the design flow analysis, and so it enables rapid design iterations and optimizations, something that is quite important for the technology nodes downscale that is happening nowadays. And finally, the analysis is design independent, meaning that the models generalize across layout without retraining as long as the resolution and the technology nodes remains consistent. However, there are of course challenges that need to be addressed for the better employment of machine learning methods in EDA. First, we need more diverse and publicly available datasets, something that Tahani also mentioned previously, that represent different technology nodes, since it is important in order to improve model robustness and scalability. Second, we should work towards democratizing hardware tools and foster innovation and collaboration within the EDA community, following the example of open initiatives like Open Road Project. And third, AI models themselves can be improved, as there is still room to refine them and thus make them more adaptable across different designs, while also expanding them to more dynamic scenarios. And finally, we need to ensure that these machine learning models integrate seamlessly with existing EDA tools, so they enhance traditional design workflows and ensure computationally affordable what-if analysis. So, to wrap up, machine learning is not just a buzzword. It's a powerful tool that can transform the way we approach critical challenges like the one of thermal analysis, that it has always been and will always be a problem, making them more efficient and more scalable. And this actually concludes this presentation, and it so happens that again next. Now, the next topic that we are going to talk about is a very interesting one, and is actually my specialty, and it's about making electromigration resilient design using computational intelligence algorithms. As technology advances, VLSI circuits are getting smaller, leading to higher current densities. While this allows for greater functionality in smaller spaces, it also introduces, of course, significant reliability challenges. One critical issue, apart from thermal analysis that we just mentioned, is the phenomenon of electromigration, or EM, as we say, where metal atoms migrate under high current densities. Over time, this can create voids and hillocks, which can eventually either break the circuit or cause short circuits, leading to IR drop and signal degradation. Traditionally, designers relied on empirical models to estimate electromigration effects. However, with the increasing complexity of modern circuits, we need more precise, maybe physics-based solutions integrated early in the design flow. And what exactly are the problems with the traditional approaches? In order to explain this, we are going to need to go back to how electromigration assessment is performed inside the interconnects and power grids. For this purpose, we have here Black's model, which calculates the mean time to failure that is caused by electromigration, where it finds the maximum allowed current density, which ensures that the design does not encounter any electromigration problems. Which means that if in a line the current density is over this current density, the maximum current density, then it may experience electromigration issues. So the engineers, layout engineers, sign-off engineers get this information from the design rules and check if the current density of every segment of the circuit does not overpass it. For this purpose, they use tools like Virtuoso Cadence or Totem Redhawk of ANSYS. In case it does overpass it, they use methods like widening the widths in order to fix it, where EM violations are. But this method has a lot of flaws, and why is that? Actually, the problem lies in two parts. The first one is how we obtain the maximum current density, and the second one is how we optimize the design in order to overcome these issues. In the first part, the academia has already solved this riddle by having widely adopted a physics-based method for electromigration modeling, that is Korhonen's equation. It is a physics-based approach that accurately calculates the stress of due to electromigration, instead of providing an imperial rule of thumb that is the mean time to failure by Black's equation. But what about the second problem? How to optimize better to mitigate better the problem of electromigration? And we need to find a more intelligent way to do that. Here is, of course, where computational intelligence comes in. And in particular, a shooting approach is particle swarm optimization. PSO is inspired by the collective behavior of biological swarms like bird flocks or fish schools. And what exactly is its mechanism is that each particle represents a possible design solution. And it based on its own best solution that it has seen in the past, and also the global best solution found in the swarm, it adjusts its position. Now, this approach is particularly well suited for problems like ours, like wire sizing in power grids, while keeping area relatively minimal, because it is well suited for high dimensional and non-linear optimization problems like ours. So the concept is to perform electromigration IR drop optimization on power distribution network lines as a proactive solution, and this is actually becoming quite crucial as the technologies shrink. In particular, the proposed method takes as inputs the power grid characteristics, the current densities, and the design constraints, and as output, it provides optimized wire sizes to balance reliability and area efficiency. This method is suggested to be integrated after place and route, where all power needs and geometry of the power grid have been determined. And by integrating this into early sign-off steps, we can proactively improve circuit reliability before fabrication. This reduces design iterations, minimize last-minute fixes, which of course cannot do much, and ensures a more robust final product. But in order to scale this approach for future technology nodes, we need to focus on 3 key areas. The first one is scalability, of course, in a way that as circuits become denser and more complex, our optimization methods must adapt to handle even larger power grids efficiently. Once again, in order to create efficient machine learning methods for this purpose, there is a need to develop standardized datasets and benchmarks for EM-aware optimization, the very large problem that EDA community has, not enough free data. Another important step is industry adoption. While research has demonstrated the effectiveness of computational intelligence for electromigration resilience, these techniques need to be integrated into existing EDA tools. By developing user-friendly plugins in already existing tools like Virtuoso and other from ANSYS that work within the standard design flow. And of course, standardizing these methodologies will also encourage their adoption in early design phases rather than relying on last-minute fixes. And finally, and most importantly, I would say, is interdisciplinary collaboration. It is essential as we need to foster strong partnerships between academia, industry, and AI experts in order to push this research forward. And by bringing this together, these diverse fields, we can develop more intelligent, automated design strategies that not only improve circuit reliability, but also enhance the overall efficiency of the VLSI design process. So to conclude, by integrating intelligent optimization early in the design process, we can ensure more reliable and more efficient circuits for the technologies of tomorrow, as the technologies are shrinking and shrinking time to time, day to day, and they are becoming more complex.
Hello, everyone. Good afternoon. I'm going to talk about the uniform thermal scheduler for deep neural network in 3D stacked systems. 3D stacked system, as the name suggests, involving stack dies together, including the cores and the memory. This architecture enables heterogeneous integration, improving the space efficiency. Different components in the die are interconnected through silicon vias, which are compact material and offering the higher bandwidth and lower latency. As a result, 3D stacked system chip alleviate the memory wall and provide the next generation computing power. However, while 3D stacked system brought significant advantages, they also introduce several challenges. For example, the manufacturing cost is high, and which make research and accelerating scientific discovery depend on the simulations. We use the state-of-art simulator called COIN for our research. Additionally, the integration of the cores and the memory in a 3D architecture increased the power density compared with the 2D counterpart. Without effective heat dissipation techniques, the heat not only transform horizontally but also vertically, accelerating the thermal conditions. Currently, there are a lot of 3D stacked chip available in the market. Leading manufacturers like Samsung, Intel, AMD, and also Apple have developed their own 3D stacked products, showcase the growing adoption of this technology. In 2D architecture, the DVFS, the dynamic voltage frequency scaling, is typically used to regulate the frequency and voltage of cores. However, this approach is insufficient for 3D stacked architecture. For example, when we run the benchmark called a string cluster at different constraint frequency, even at the 1 gigahertz, the peak temperature will exceed the thermal threshold at 75 degrees Celsius. Furthermore, running tasks at such low frequency will significantly reduce the system's performance, highlight the limitation of the DVFS alone for the core in managing the thermal challenges. So thermal management in 3D system generally involves controlling the behavior not only for the cores, we also need to take actions in the memory banks. For process, DVFS is dynamically coordinate the frequency voltage, but we also need to reduce the active behavior of the memory bank. So I will give you a motivational example. We have two scenarios, and in scenario 1, we just let the core run at 4.7 gigahertz without placing any memory bank to the low power model. In the scenario 2, we put the first 14 memory bank into the low power model, and we control the core frequency set to 4 gigahertz, and then we show we can clearly see the first scenario. They can hard to meet the thermal management, the thermal constraint, and with sacrifice not of performance. The second scenario, we combine the memory, the low power model for the memory bank and also the DVFS for the core. Then we coordinate it together, and we can achieve the good system performance. This is the implementation of the low power model. I will not go into too much details about the low power model implementation. And the key points is when the power bank is switched to the low power model, then the data is keep it in situ without any migration. And but this constraint, when the memory bank is switched to the low power model, this data is inaccessible, and we only need to consume a tiny part of power to keep this data. And if we want to re-access the data, then we need to reactivate this memory bank and fetch the data, which increase the latency. So this low power model design is also not free. Then how to propose a unified scheduler. On the one hand, we should do the DBFS for the cores, and on the other hand, we applying the low power model for the memory bank. Then we devise a deep Q-learning method to do that. Because of the design space is huge and is exponentially large, then we use the embedding space to compress this design space. Like the large language models token, they use the embedding space in the hidden space to compress the language token. We borrow this idea and into this design space, and we also design a very tiny neural network for predicted Q value, and the result shows the compaction of the embedding space is effective. We also verify our approach not only for the classical, PASIC, and the Splash 2, that kind of classical benchmark. We also verify it in the deep neural network like AlexNet, ResNet, and it works very fine, not only for the performance, also for the energy consumption. So let's draw the conclusion, and we propose a unified scheduler not only for the core, but also for the memory bank to do the thermal management for 3D stacked architecture, and we achieved a good performance while keep the system security safe, thermal safe.
I think we can proceed to the questions for all the different presentation in the aspects. So all of you can write also in the QA session or raise your hand to get your microphone unmuted. Just a quick question from my side. It was more on what to Tahani about the presentation regarding the began sorry, the hotspot lithography. So
in which slides?
Maybe if yes, in the previous slide. Sorry.
This one?
No. I mean in the first part of the presentation before the began. In the convolution neural net of hotspot detection. So I think it's in the second part of the talk, a bit
after the break. Yes.
Exactly.
Okay.
Here, exactly.
Yeah.
So, Tahani, my question was, did you have any specific convolution neural net like AlexNet, or it was some architecture that the proposed method seems to work better than the others, or they provide some intuition about the convolution neural network that they take?
Actually, this depends on the kind of data set that we treat with the convolutional neural network. For example, in this paper, they preferred to build like neural network from the scratch in order to be very well fit to the problem. But actually, also they suggested to use the transfer learning by using network or any other valuable model to be used. But actually, this is different from problem to problem. But here they preferred to use like model building from the scratch according to the data set.
Okay, thank you very much for answering. And one more question to Olympia. So for this particle swarm optimization, my question was, have you considered having some other methods, some other computational methods like genetic algorithms or different optimization methodologies? I think, Olympia, we cannot hear you.
Sorry, thank you very much. Yes, actually, this is a very interesting topic. Yes, there are other techniques that have been explored in the area of electromigration hardware design. Genetic algorithms, for example, is a very powerful optimization tool. And the thing is that genetic algorithm is inspired by natural selection, mutation and selection crossover in order to evolve to better solutions over multiple generations. And PSO, particle swarm optimization, on the other hand, and this is the reason why we have chosen this method, is based on collaborative learning. Where candidate solutions particles adjust their position based on both their own experience as well as the swarm's best known solution. So particle swarm optimization tends to be faster and actually more efficient to find the best solution, since the first genetic algorithm can introduce randomness due to the mutation and selection. But the thing is that a very interesting approach would actually be to combine these two, in order to make the optimization problem better, because we can combine the mutation and selection in order to explore more in a better way the search space, and on the other hand, PSO in order to be more efficient to convert into a specific solution. So yes, actually, that was a very nice point. Thank you for the question.
Thank you, Olympia. We have two questions in the chat. I think both are for Tahani. So the first is since there is a data scarcity, how do the data diversity is ensured? Is there any occurrences of bias?
Yeah, thank you. This is a very interesting question. Actually, when we talk about the source data that been used on the training, and after that we used a few data for the fine tuning. In the first stage, which is when we use the source data to the training, it actually include a lot of different images for the urban satellite images, and this can help to increase the data diversity. But actually, when we talk about the fine-tuning stage, if we are so lucky, we will have different benchmarks for 10 different. If they are almost the same, we could have kind of bias, but it's not will be a big issue, because we always try to generate data suitable to the main goal or the target data. So in this case, actually based on the data available in the fine-tuning stage. But actually here in the fine-tuning stage, almost the data, it's not the same, it's more diverse. So it could be a little bit away from the bias.
Perfect, thank you. And I think there's one more question in the chat. So the question is about the quality of the generated data by transfer learning in the began presentation, and if there are techniques that ensure the quality in comparison to real data.
Actually, the quality of generated data, it's based on the quality of the model and the amount of data that have been used on the training. In the first few, could have very bad quality data, but actually after, for example, 10,000 rounds or more, we have more quality data, or actually very typical data to the real data, because every time we train the model for example, 10,000 or 20,000 rounds, we improve the quality to become very high, to generate images very close to the real images. So it will generate very high quality images.
Thank you, Tahani. I think also there's a question regarding Olympia. So why is the hardware world so behind in having strongly established open source alternatives, and what can be done to achieve that, and how would that affect academic research on this field?
Yes, actually another very nice question. Traditionally, EDA is very behind in open source adoption, actually, in general, and there are a lot of barriers for that. First things first, not a lot of people do hardware, and specifically EDA. So apart from that, the thing is that it has high complexity and cost. The workflows for EDA are multi-stage and extremely complex that require precise modeling and verification and fabrication considerations. So it requires significant resources and expertise in order to do that, which makes the pool even smaller. Also, it's the fact that there is foundry, the proprietary foundry processes. And the thing is that the PDKs belong to some companies and they are generally not openly available. And so the EDA community cannot leverage from real world applicability. And this is also a problem for research in general. And that is why Open Road and such projects actually exist, and that is why the democratizing hardware, as we can see, slide 39, if you please, Yixian, go there. That is why the slogan 39.
30.
Thank you. Yes, thank you very much. And that is why it is the slogan democratizing hardware design. There is an extremely large need in order to have more open source hardware design and EDA tools in order to make research more available, actually. I hope this answers your question.
Thank you, Olympia. Thank you for the answer. I think we have one more question from the audience. I think Mr. Athanasios Touvaras, you can unmute your microphone.
Thanks, George. First of all, hi everyone, and thank you very, very much for these wonderful presentations. I have two questions. The first one is for Dr. Tahani and considers this convolutional neural network that processes images. And I was wondering your take, Dr. Tahani, on the resolution of such images. So, for example, what happens if we have some data with low resolution images? Does it seem that contemporary neural network architectures can withstand that level of noise, or will our results get deteriorated so much that they will diverge from the ground truth? This is the first one.
Can you repeat the last part of the question about the image noise, please?
Yes, sure. So what happens if the image resolution is low? Does the neural network, the convolutional neural network, can it deal with that noise? It's not exactly noise. Let's say low quality data due to low resolution. Can the neural networks deal with that, or do their outputs deteriorate much?
Actually, this will not affect a lot of the model, because when we deal with convolutional neural network, we move the image for the gray level to be like all the colors between the white and black, and the important feature, it will be like more like very clear, and the not important feature, it will not be appeared. And also when we deal with the convolutional neural network, the convolutional neural network actually did something called like the feature extraction, and try to extract the main important feature. As we can see here in this figures, we will deal actually with pixels in the gray level, and so extract the main feature from such images. It will be much more easier than dealing with images when in like 3 types of colors or only different kind of images. So in this case, it will not be like very issue the quality of images, especially if we have like such kind of patterns. It's not very complicated patterns. It can be easy to define, and it can be easy to have it like very clear compared to the noise.
I see. Thank you very much for your response. The next question is for Dr. Shen. So there was a slide, I don't remember the name, where a deep learning model, if I am not mistaken, was used. And I would like to elaborate a bit on the usage of it. For example, was it for decision-making purposes? Was it for scheduling purposes? Perhaps you said that, but I lost it on the whole presentation. Could you please repeat why a DQL model was used? What was the purpose of it?
Yeah, so the DQA model is used to capture the low power model for the memory bank, and the DVFS for the core. The DQN is trying to learn the cooperation, the coordinate, the integration of these two actions. And when this model is trained, and we compile it to the binary file and put it to the commit for the scheduling. The DQM is like an agent, like a scheduler.
Okay,
Yeah.
okay. Thank you very much.
Yeah.
Thank you all for the question and the answers. So are there any other questions? So if there is no other question, I would like to thank you for your participations in the webinar. And I think this was the first webinar of our series. We're going to have another 2 webinars with more content. We're going to upload the slides to have them publicly available on our site on COIN-3D project. So thank you very much for attending, and hope to see you also in the other webinars as well. So have a nice day all, and good afternoon.